Okay, hello everyone, and welcome back to the Semantics and Verification course. Today we're going to start a completely new module, so we are done with this whole work on semantics, and now we're getting more into the verification part. Let me share my screen. Okay, so before we start, I have a couple of announcements. Well, more than a couple, 3 announcements. So the first thing is that all of you will get feedback on your first homework if you have already submitted it by the end of tonight. So if you didn't get anything by the end of tonight, your homework might have ended up in spam folder or something, just send me an email. The second point is that now that we are finished with the first module of the course, with the semantics module, I have prepared a very short survey that you can access on Canvas, and I would really appreciate it if you just take part in that. So it basically asks you what's going on well and what's not going on well, so that I can change the rest of the course based on your needs and your interests. And finally, the last point that I wanted to say is that I'm setting some bonus points. Basically, I'm setting 5% bonus points for people who would take part uh, in discussions during the sessions. So try to speak up, and the 5 top people who speak the most during the whole course will get 5% added to their grades. Okay, and today I'm going to talk about a completely different view to verification, and this is the framework of two-player games on graphs. And basically, we are now leaving the realm of semantics and no longer talking about what a program means, but mostly talking about how to verify the correctness of a program. And this new module is mostly based on an unpublished book by Krishnendu Chatterjee and Jean-François Raskin. So we wouldn't have any additional material for this part, but I try to make the lectures as self-contained as possible. Okay, let me also open the chat box so that I can see if anyone sent a message to me. Okay. So let's start. So let's start by defining what we mean by a game. So the kind of games that we are going to look into are games that are played on graphs. And a game graph or an arena is basically a tuple, and it contains basically a finite directed graph, which we show with the set of vertices with V and the set of edges with E. And also, because it's a two-player game, the set of vertices is partitioned into 2 different sets, V1 and V2. And the intuition behind this is that we think of V1 as the set of vertices that belong to player 1, and we think of V2 as the set of vertices that are under the control of player 2. Okay? So for example, here's a simple game graph. Don't mind the labels right now. It basically is a directed graph, and there are 2 types of vertices. So I show the player 1 vertices, for example, with circles, and the player 2 vertices with squares. And so the idea is that you begin the game at some point at one of the vertices of this graph. Let's say we start here. And then the player who owns the current vertex decides which edge to traverse. So from this current vertex, the player that owns it, the square player, chooses whether he wants to take this edge or this edge or this one. And then when this happens, we go to a new state, or we might stay in the same place. And let's say we went here. And then the owner of this new vertex decides where we go next. So which outgoing edge we take out of this current vertex. So the circle player can choose to go back to 0, 0, or to go to E, or to go to square 0, 1. And the game just goes on forever. So this is basically an infinite duration two-player game. So the idea is that we play for a very long time, for infinite time. And based on this, we can actually define some vocabulary. So you definitely know what a path means. A path is basically, well, a path in this graph, which is like a sequence of vertices and edges such that every two vertices coming after each other are actually connected by a directed edge. So for example, a path here would be this. And in our paths, we also allow them to have repeated vertices and edges. So for example, I can start from here and then have a path that just goes here for a finite number of steps. So that's the definition of a finite path. And then an infinite path is basically the same thing, except that it's infinite. It goes on forever. So when the two players start playing on a graph game like this, of course, we start at a given starting vertex. Let's say we start here. And then their interaction basically gives us an infinite path. That is the path that they traverse over this graph. And this infinite path is called the outcome of the game. So the outcome of the game is basically the infinite path that is traversed when the two players are playing this game. Okay. So until now, the only thing that we know is how players actually play, but we don't know what they want to do, what their objectives are, and how they can actually win the game. We need to define that also, and we need to define it formally. So let's define what a winning objective is. And sometimes I don't say winning objective, I just say objective. But these two are the same. So an objective is basically a set of infinite paths. I don't know why I've written a sequence. It's a set of infinite paths. So you can think of it like this. As player one, you can have an objective, which is basically a set of paths, a set of infinite paths that you like. And you want to try to play this game so that no matter what player two does, the outcome of the game becomes one of the paths in your objective, right? So you have a set of desired paths, a set of favorite paths, and you want the outcome of the game to be inside that set. And it's actually quite important to be very concrete about what is finite and what is infinite in these cases. So our graph, our arena is always finite. The paths that we look after, and the outcomes of the game are always infinite. So the outcomes of the game are always infinite paths. And then when I say that a winning objective is a set of infinite paths, this objective itself can be an infinite set as well. So the objective does not have to be just a finite set of paths. It can be infinite, it can be uncountable, it can be anything. Okay. So each player can have an objective, and then we say that a game is zero-sum if the objectives of the two players are basically complements of each other. So if the objective of player one is, let's say, O, then we want the objective of player two to be all the infinite paths that are not inside of O. So if this holds, then we say that the game is zero-sum. The idea is that if you have a zero-sum game, you always have a winner when you know the outcome, right? So either the outcome is in the objective of player one, in which case player one has won the game, or the outcome is in the objective of player two, and player two is the winner. Okay. So this is a very abstract definition of what an objective is, but we will then later on during this course see many different types of objectives, and we will actually work on finding strategies for achieving each of these objectives. But here are some of the classical objectives that we will definitely see in this course and have a lot of applications in verification. So before I define the objectives themselves, I have to define two sets. So let's say that I have an infinite path row, and let's say that I show it with row 0, row 1, and so on, and these are basically vertices of the graph. So my path can be, for example, 0, 0, 0, 1, 0, 1 square, so on. So I define two sets with regards to this infinite path. The first set is the visit set, which is basically, as the name suggests, the set of vertices that are visited by this path. So this is the set of all vertices in V, such that there is an index in my path row, such that the vertex is equal to row I. Okay, so this one is easy. The second one is a little bit more complicated, but it's also very easy. So we call this the infinite visit set of row, or the infinite set of row. And the idea is that it basically consists of all the vertices that are visited in my path row infinitely many times. So you forget about any vertex that is visited only finitely many times, and whatever remains are the vertices that we have seen infinitely many times, and those are in inf of row. And well, one way to define this formally is as follows. So you can basically say that this is the set of all vertices in V, such that there is no index I, such that if we just look at the subpath or the postfix from starting from I and going to infinity, it does not visit V. So the idea is that after each index I, there is another index where we have visited the vertex V. So the vertex V has been visited infinitely many times. Okay. So are there any questions about these two, or are they clear? Okay, great. So now based on these, we can actually define our classical objectives. So let's say that we have a set of target states, which we call T, and these are basically a subset of vertices. So I'm marking some of my vertices as T, or target. Now, some of the classical objectives that we will look into are the following. So the first objective that we look into is safety. And basically what safety says is that I want the game to always stay within my set T. I want to make sure that I never leave T. Okay. So for example, let's say that you are the square player here, and let's say that this is an error and you don't want to reach this error. And let's also assume that the game starts here. If the game starts here, because you're the square player, you can decide to take this edge and just remain in the same vertex. And you can just do this forever. So if your objective is to be safe in these vertices, so basically if your objective is to not visit E at all, then as the square player starting from this vertex, you can achieve this objective. But if you're the square player and the game starts from this vertex, what happens? That's also very similar. So, and the game starts from this vertex, what happens? The thing that happens is that the other player can directly just go to the error state, and then you cannot achieve this goal. So the safety objective basically says that you always remain in a designated set of safe states, which is the set T. Now, the dual of this objective is reachability. So reachability of T says that you have to visit T at least once in order to win the game. So let's say that you are, again, let's say that you are the square player and you're starting from here. And let's say that this time you actually want to reach the error state E. Can you achieve that no matter how the other player plays? The answer is no, because, well, you have to either go to 1, 0 or to 0, 1. And in each case, the other player can just send you back to 0, 0 and avoid you getting to the error state at all. So as the square player starting from here, you cannot achieve reachability of E. Okay. But if you start here, for example, as the circle player, you can of course achieve reachability of E with just one step. Okay. So these are the two most classical ones. But we also have some other objectives that are kind of more interesting. And as we go on during this course, you will see that they're also a bit harder to solve. And these are the objectives that are named after the mathematician or the computer scientist who came up with them. And this is what we call basically Buki objectives. So the original German pronunciation is Büchi, but that's too hard. So everyone just calls it Buki. So the idea behind Buki is this. Let's say that I have a target set T, and my goal is to visit T infinitely many times. So I want the set of vertices that are visited infinitely many times to intersect the set T of target sets. Okay, so in this case, let's say that you're the square player, and let's say that the set T is 0, 0, and E. So these two are your target sets, and you're the square player. And let's say that the game starts here, right? So first, the circle player makes the move. It can go here, or it can go to E. If it goes to E, you will just remain here forever and make sure that you are visiting E infinitely many times by just going through this edge here infinitely many times. So you get your Buki objective. If it goes to either side, then this is also kind of similar. You go up here, and then if it goes to E, you can just cycle here. But the main problem is what happens if you go here and then the circle player sends you back. And then you go here and the circle player sends you back, or you go here and the circle player sends you back. So in this case, you cannot actually achieve Buki from every state. At least you cannot achieve it from this state, because the circle player will just keep you here. So what this means is that basically the other player can achieve Kobuki. And the idea behind Kobuki is that you want to have this. You want to have every vertex that is visited infinitely many times be a subset of your target set, be in your target set. So what this means is that after finitely many steps, you want to be inside the set T, and you don't want to leave it anymore. So this idea that every vertex that is visited infinitely many times is in T, this is basically equivalent to saying that for a few steps, for finitely many steps at the beginning of my path, I might not be in T, but at some point I will enter T and I will remain there forever. So this is the Kobuki objective. Okay. And one thing that I'm sure you have already seen or you have already guessed is that reachability and safety are duals, and so are Buki and Kobuki. And what I mean by this is that basically reaching T is the same, is the set of vertices, let's say the set of infinite paths that reach T. So I'm looking at this as an objective, as the set of infinite paths. The set of infinite paths that reach T is the complement of the set of infinite paths that are safe in V minus T, right? And this is, again, very easy. So you either, if you consider an infinite path here in your graph, it either reaches T, in which case it's here, or it doesn't reach T, which means that it has always remained in the vertices that are not in T, which is safe of V minus T. And the same thing also holds for the infinite case, for the Buki case. So Buki of T means that you want to visit T infinitely many times, right? And Kobuki of V minus T means that you want to visit T only finitely many times, because at some point you want to stop seeing T and only see V minus T. So it's also obvious that Buki of T and Kobuki of V minus T are complements. So we have this kind of duality here between reachability and safety, and also between Buki and Kobuki. Now, what this tells us is that basically when we are looking into algorithmic ideas for deciding which player has a winning strategy, which player can, for example, enforce reachability, we just need to find algorithms for reachability and Buki, and the algorithms for safety and Kobuki are just the same thing, except that you just flip a bit. So in the remainder of this course, I am mostly going to just talk about reachability or Buki, and just assume that you know how to turn this into safety and Kobuki. Okay. And then there is also yet another classical objective, and this is probably the most important objective ever. And this is the parity objective. The parity objective is a bit more complicated, and I'm going to go through it. And it might seem very unintuitive at this point, but I assure you, as we go on through this course, you will see that this is actually a very useful concept. And you will see that many verification problems end up reduced to deciding the parity on the parity objective on something. Okay, so the idea behind parity is that you have some priority function that assigns a priority to every vertex. So you assign a priority, let's say between 0 and D, to each one of your vertices. Okay, and then the objective, which, well, remember that this is an objective, so it should be a set of infinite paths. The objective parity of P, and P is this function, is defined as the set of all paths rho such that the minimum parity that is repeated infinitely many times, the minimum priority that is visited infinitely many times in this path rho is even. Okay? So I'm basically assigning priorities to each one of my vertices, and then the game has an outcome. And in this outcome of the game, I'm going through an infinite path. So I just go through this infinite path and count how many times I have seen each of the priorities from 0 to D. And then I discard all of those who were seen finitely many times and only keep the priorities that were seen infinitely many times. And among these, I look at the smallest. And I want this smallest number to be even. So this is the parity objectives. As player one, I want to ensure that the smallest priority that is visited infinitely many times is even. Okay? And actually, parity is the most general objective that we will study. Let's actually try to prove this first. So can you show that Buki and Kobuki are special cases of parity? So going back here, consider this. Buki of a set T, and T was a set of vertices, is basically the set of all paths that visit T infinitely many times, right? Now, can you encode this as a parity condition? Well, in order to do that, you should just give me the function P, the priority function. So can you give me the priority function in chat? So basically, I have a set T of vertices, and I want to visit this set T infinitely many times. How do I turn this to a parity condition? And in the parity condition, I have to basically assign a priority to every vertex instead of just taking a subset of vertices. And then I want to have this condition. I want to know that the minimum parity that is visited infinitely many times is even.
Sorry, what do you mean by priority? Isn't it?
Oh, priority is just this function. So I have a function P, which is assigning a priority to every vertex, right?
Okay.
I call this a priority function, and this is part of my input, let's say. And then I define the parity objective parameterized by this function P. So parity of P is the set of all paths, all infinite paths, that if you take the priorities that are visited infinitely many times in these paths, the smallest such priority is even.
Okay. Okay, I got
Okay,
it. Thank you.
great. Okay, in the chat, we actually have a response for this. So Yuan is saying that we can just say that the priority of a vertex V is 0 if V is in T, and otherwise the priority of V is 1. Yes, so let's just copy this Bookie objectives definition. And okay, so this was the definition of Bookie. And the idea here was that we have a set T of target states, and we want to take all the infinite paths that visit T infinitely many times, right? Now, if we use the function that Yuan is proposing here, it's basically saying that give priority 0 to every vertex V that is in T, and give priority 1 to every vertex V that is not in T. Okay. Now, if I satisfy the Bookie condition, then it means that I'm visiting T infinitely many times. So priority 0 is visited infinitely many times. So I satisfy the parity condition. Now let's do the other side. If I satisfy the parity condition, it means that my smallest priority is even. The only even priority is 0. So I have visited uh, priority 0 infinitely many times. So by definition, I have visited T infinitely many times. So Bookie of T is the same as parity of P when P is defined like this. Okay, what can we do with Ko-Bookie? Can we write Ko-Bookie as a parity condition? So let's go back to Ko-Bookie. So the idea of Ko-Bookie was that we have a set T, and we want to make sure that we go outside of T only finitely many times. So we want to make sure that every vertex that is visited infinitely many times is in T. Or in other words, we want to make sure that the vertices that are outside of T are seen only finitely many times, or we want to make sure that there is some point from which we will not see anything outside of T anymore. Okay. So now can you tell me how to encode Ko-Bookie as a parity condition? So this was the encoding of Bookie. How can I encode Ko-Bookie? So again, I want you to just give me the priority function P. And also remember that Ko-Bookie was basically what? It was the dual of Bookie, right? So we had this connection between Bookey and Kobuki. Yes, we can just use the inverse of what we had before. We can say the priority is 1 if the vertex is in T, and the priority is 0 otherwise. Right? So why does this work? So let's say that some infinite path is in Kobuki of T. Then what does that tell us? It tells us that it basically visits the vertices outside of T only finitely many times. But the path is infinite. And if it's visiting the vertices outside of T only finitely many times, then it has to visit the vertices in T infinitely many times. So basically, it's visiting the vertices with priority 0 only finitely many times, and vertices with priority 1 infinitely many times. So it also satisfies parity with this priority function. And the other side is also very similar. If it satisfies parity with this priority condition, then it means that uh, basically, oh, not really, right? Is this correct? Let me see. Okay. So let's just go through this. If it visits, if it satisfies this parity, then what it means is that the minimum priority that is visited infinitely many times is even, right? So the vertices that have priority 0 are visited infinitely many times. Okay, no, this is not good, right? Because we want the vertices that are visited infinitely many times to be in T. Yes. So we just have to change the parity because we are hard coding this evenness here. And because we are doing that, then we can just change this to oh, we can just change this to 1 and 2 so that we can also handle the minimum thing. So now, if the minimum, no, this is 2 and this is 1. Okay, so if the minimum parity that is seen infinitely many times is even, then that means that we have seen 2 infinitely many times and we haven't seen 1 infinitely many times. Because remember that this is the minimum priority that is visited infinitely many times, right? And this means that basically I have seen everything outside of T only finitely many times. Okay. So we can basically define both Bookey and Kobuki in terms of parity. And now if you look at this, it's basically just fidgeting with the priority function. And we can do this with parity itself. So parity is its own dual. How can I write this? So parity of P, if I want to take its dual in a manner similar to this, what would that be? So parity of P is the complement of what? Of parity of what function? So let's say Q. Can you just give me Q? So here we saw that reachability of T is basically the complement of safety of V minus T. Bookey of T was the complement of Kobuki of V minus T. And we saw that both of these can be written as parity. So now the question is, can we do this kind of dualization on parity? Can we say that parity of P is the complement of parity of some other function q, some other priority function q. And if we can, then what should the value of q be? Can you define q? It's actually very simple if you think about it. So what is parity of P? Parity of P is basically the set of all infinite paths in which the value of P that is visited infinitely many times, the smallest value of P that is visited infinitely many times is even. So if we take its complement, it would be basically putting odd here. So all we have to do is to make sure that the function Q changes the parity. So it can be 1 plus P. Right? And then parity of P is basically the complement of parity of 1 plus P. Okay, are there any questions? Is everyone clear on how parity works? Okay, so no questions, that's fine. Now, finally, another thing that I just want to define here is the notion of tail objective. And basically, we say an objective O is a tail objective if it does not depend on finite prefixes of our infinite paths. And what that means formally is that whenever a path rho is inside my objective, I want to be able to just cut off its first I minus 1 vertices and get the path from row from index I forward. And I want this postfix to also be in my objective. So it's actually very easy to see that parity, Buki, and Kobuki are all tail objectives, right? Because they all talk about the vertices that are visited infinitely many times. So if a vertex is visited only finitely many times, it doesn't really matter in parity. And it also doesn't matter in Buki and Kobuki. They are all based on this inf set. Now, the fact that they are only based on this inf set means that if I have some infinite path that satisfies that is inside my parity objective or inside my Buki or Kobuki objective, then I can basically chop off a finite prefix of it, and then the rest of it will also satisfy in the same objective. Right? So these kinds of objectives are called tail objectives because they just care about the tail of the infinite path. Okay. Now, is reachability or safety tail objectives as well? Are they tail objectives as well? So they are not tail objectives. Why? Because you might have a case where you can reach a vertex only once. And then if you remove a finite prefix of your path, and this finite prefix contains the one place where you have reached this vertex, then of course the remainder of the path is not in your objective. So what this shows you is that you cannot actually directly encode reachability and safety as parity. So it's not just that you can set some parity function P and then parity encodes reachability or safety. But actually, as we will go on, we will find other ways that by simple changes to the graph itself, parity can actually also handle reachability and safety. But for now, what I really want you to know is that because parity is a tail objective and reachability and safety are not tail objectives, you can't just set a priority function and make this into reachability and safety, whereas we could do this for Buki and Kobuki. Okay. So where are we now? We defined what a game is. We defined how the two players can play on these games. And we also defined what an objective is. So we kind of know when a player has won the game, right? So from a mathematical point of view, we are at a point where if we have the outcome of the game, if we know exactly which infinite path was traversed in the game, then we can say who has won. But this is still not quite good enough. We like to also talk about strategies. And a strategy is basically what you would imagine from the name. It's a way for a player to play so that uh, he or she always wins, right? But we want to actually make this much more formal and give a mathematical definition of what a strategy can be. So let's say that I take one of my players. Let's say I took player I. So I is either 1 or 2. And then a strategy for player I is basically just a function. And this is a function from v star times vi to v. What does this mean? Well, the v star part, well, if you're familiar with this kind of expressions, v star basically means a finite path, a finite sequence of vertices. So what a strategy sigma I gets is some finite set of vertices, W, and also some other vertex, which has to be in Vi, and this is V, right? So this whole thing, the paths that we have taken until this point in the game and the final vertex are basically the history of the game. The idea is that each strategy is basically a recipe that gets the history of the game, says that, okay, the game started at this point, we went through this path, and now we are in this specific vertex. And then based on that, decides where to go next. And we say that the strategies should respect the edges of our graph, which basically means that, well, for example, if the path that you went was something like this, oh, sorry, you can't go there, something like this, let's say, and you are now at this vertex and the square player has to play, then the information that he has is the whole history of the game. He knows that the game started from here and went all the way until here. So this is what's encoded in V star. And there is a final vertex in VI, which says where we are right now. And based on this information, the strategy tells us where to go. And it can't tell us to go somewhere that is not an edge, right? So from here, it can only tell us to go here or go here. So that's basically the definition of a strategy. So now let's see what we need to fix in order to have a unique outcome. Well, if we fix a strategy for player 1 and a strategy for player 2, and if we are sure that they will just follow these strategies, then can we be sure that we have a single outcome? Not necessarily, because we have to also fix the initial state. So if we fix 3 things, so the initial state or the initial vertex, and the strategy of player 1 and the strategy of player 2, then of course the game proceeds in a very deterministic manner and we have a unique outcome. And again, if the strategy of player I is sigma I will show this unique outcome by outcome of V sigma 1 sigma 2. So this basically means the infinite path that is obtained if we start the game at vertex V, and if player 1 follows a strategy sigma 1 and player 2 follows strategy sigma 2. Okay. So now let's talk a little bit about the strategies themselves and what kind of, what types of strategies we have. So by definition, a strategy is simply a function. and you can have a lot of different functions, right? So you can basically have infinitely many different strategies for each one of your players because the domain here is infinite. So V star is infinite. Now, but in most use cases, we don't really need the most general type of strategy. It is usually the case that we can basically always find a simpler type of strategy. And we are actually interested only in two types of simple strategies, but I'm going to define the three classical types here. First of all, we say a strategy is memoryless if it only depends on the last vertex. So a player is playing a memoryless strategy if he always ignores the history of the game. And whenever he wants to choose where to go next, the only thing that he looks at is where am I right now, right? And mathematically, we can basically say that this means that the strategy at WV, and remember that W was the path that we have taken until this point, and V was basically the final vertex that we are in. So the strategy is memoryless if sigma of W and V is sigma of W prime and V for any path W and W prime. In other words, we don't really depend on the path that we have taken until this point of the game. We only care about what vertex we are in. And sometimes when we are talking about memoryless strategies, we just assume that they are functions from vertices to vertices because, well, they don't depend on the path, so why bother with keeping it here at all? So we can just get rid of this when it's memoryless. Okay. Another related concept is the concept of persistence. And the idea behind persistence is that you basically don't change your strategy in the sense that if there was a path that got to some point, so let's say I had a path W and I got to a vertex V. For example, I started from here, I came all the way to vertex 11 here, or vertex 1, 1 here. And let's say that my strategy, the circle strategy, told me to go to 0, 1. Now, let's say that the other player played this whole thing again, and we came back to the same vertex after going to 0, 1. Then I'm persistent. I will take the same strategy out of this vertex. So to make this more mathematically well-defined, it basically means that whenever we have two different paths, W and W prime, and this is the prefix symbol. If W is a prefix of W prime, then I will have the same strategy at WV and W prime V. So this is the idea that WV is when I started for the first time and I came to this vertex. And at this point, the circle strategy, the circle player's strategy told me to go here. And W prime is basically the continuation. So I started from here, did this, and then continued on and came back here again. Right? So W is now a prefix of W prime. And because W is a prefix of W prime, and because they end in the same vertex V, I have to choose the same strategy that I had chosen before. So I have to be persistent and go here. This is the definition of a persistent strategy. And finally, the definition of a finite memory strategy is also very easy. So if you consider general strategies, they have infinite memory. They're basically remembering the whole history, right? And now if your strategy is encodable, let's say in a Turing machine that has finite memory, then this is a finite memory strategy. So I don't want to go into the detailed definition of finite memory strategy, but the only thing that I want to say here is that it doesn't mean that you remember finitely many of the previous steps. What it means is that you basically have some sort of, let's say, RAM memory, and you can write finitely many things in there, and you can write whatever you want. So think of a finite memory strategy as a strategy that can be run on, let's say, a machine with finite RAM. Okay. But in this course, we are going to mostly work with memoryless strategies and to a lesser extent with persistent strategies. So most of the time you will be fine with just thinking of a strategy as a memoryless strategy, which is this. Okay, now in our definition of strategies, they weren't actually that useful because what we were saying was that a strategy is basically just a function that tells you how to play. But what we are actually interested in is when this strategy is useful for winning the game, right? So a strategy is a winning strategy if it wins you the game, of course. That's the simplest definition ever. But if we want to make this mathematically concrete, what we can say is that, let's say that we have the same arena that we always have. So we have a graph and it's divided into two parts. So player one owns some vertices, player two owns the other vertices. And let's say that I also have an objective O1 for player one. So remember that objectives were basically sets of infinite paths. So I have an objective for player one and I have the graph. And I also know the initial vertex. I know where I'm going to start from. I'm starting from some vertex V. Based on this information, a strategy sigma 1 for player 1 is a winning strategy if it wins no matter how player 2 plays. So no matter what the strategy of player 2 is, the outcome of the game would be in the objective of player 1. So remember that I defined this outcome as the infinite path that starts from V and is achieved by the players playing according to sigma 1 and sigma 2. So a winning strategy for a player is basically a strategy that leads to the infinite path, the outcome being in the player's objective. And this holds no matter what the other player does. So no matter how the other player plays, you get the outcome in your objective and win the game. So based on this, how do you prove that a strategy is not a winning strategy? Well, in order to prove that, for example, sigma 1 is not a winning strategy, all it takes is for me to give you a strategy for the other player, give you a sigma 2, such that the outcome is not in the objective. And this kind of strategy is called a spoiling strategy. So sigma 2, which is a strategy for player 2 to play, spoils sigma 1, or is a spoiling strategy for sigma 1 if the outcome of running these two is not in the objective of player 1. And of course, well, I define these things only for player 1, but you can just swap the 1 and 2 and define the same things for player 2. So you can define a winning strategy for player 2, and you can also define a spoiling strategy in the very same manner. Okay. And well, again, by definition, a strategy for player 1, sigma 1, is a winning strategy if and only if it doesn't have a spoiling strategy, right? So either there exists a spoiling strategy sigma 2 for sigma 1, or sigma 1 is a winning strategy. Okay, but even this is not quite enough, because see, the way that we defined this was that we fixed our initial vertex. We said starting from an initial vertex. So what's much more interesting for us is to see from which initial vertices we can actually have these strategies. And this is what we call a winning set. So let's say that I'm player 1, and let's say that I have some objective O1. My winning set is the set of vertices such that starting from those vertices, I have a winning strategy. And I show this with the win set, basically, of a given objective. So in this case, I is again the number of the players, so it's either 1 or 2. So win 1 of objective 1 is basically the set of all vertices, such that if the game starts from those vertices, player 1 has a winning strategy with regards to objective one. And now here's another really important definition, and this session is mostly about definitions, but hopefully we can also see an algorithm soon. We say that the game is determined if the winning sets of the two players are complements of each other. So it basically means that we, we can divide the vertices in two sets. For example, these are the vertices in which player one has a winning strategy, and these are the vertices in which player two has a winning strategy. So the game is determined if starting from any vertex, either player one has a winning strategy or player two has a winning strategy. Okay. So do you think that all games are determined? Or can you come up with an example of a game that is not determined? That's actually a good question for a homework. I would probably leave it to you for a homework. There are actually many games that are not determined, but I'll let you find one. So for now, let's just take our very first objective. Let's take reachability and see how we can find the winning sets for reachability. So in this case, suppose that player one is the circle player. And let's say that the objective is to reach the error state. So player one wants to make sure that we reach this state E. What are the winning states for player one? So starting from which of these vertices can player one force the game to visit E? Okay, we have some answer here, but well, I want to do it a little bit more systematically. So what I want to say is that, first of all, if you start the game at E itself, you have definitely visited E, and player one has definitely won, right? So E itself is definitely in the winning set of player one. Now, what else is in the winning set? So player one controls the circle vertices. If we are in 1, 0, 0, 1, or 1, 1, what happens is that we can basically, player one controls it and can just directly go to E. So in other words, these are also winning states for player one. I think what's in the chat is actually correct, yes. So, but how did we get this? Well, if you have any circle, any vertex that is under the control of player one and has an edge to E, then that's of course in the winning set of player one. But then what happens in the other cases? So we know that right now, what we know is that if the game starts here or here or here or here, player one wins. But if the game starts anywhere else, for example, if it starts here or here, then player two has no chance but to go to one of these states. And then from there, we know that player one wins. So basically, any square with all outgoing edges to one of these previous cases that we know player one wins, right? So these are also states where player one wins. So for example, starting here, player two plays first because this is a square, but it has to go either up or down. And no matter where it goes, we already know that the other player has a winning strategy from there. So these are all in the winning set of player one. But crucially, this last vertex is not in the winning set. Because starting from here, player two can just take this self loop and stay in this vertex forever and make sure that we will never reach E. Right. Okay, so can we extend this to the general case? Well, yes. So suppose that the objective for player one is to reach a set T. We basically define something which we call attractor. And the idea behind it is very simple. So I want to define a sequence of sets. And my initial set is just my set T that I want to reach. And then at each state, at each step, I just used what I know until this point to create a new set. So what I know until this point is that if I start from A0, I can reach T and I win. So another way of winning is that if I'm in a vertex in V1, so this is a vertex under the control of player 1, and it has at least one successor in A0. If this is the case, then player 1 can just go to that successor, and then we are in A0 and player 1 wins. Or the other case is that if the current vertex is under the control of player 2, but no matter what he does, he ends up in A0. So no matter what he does, no matter where he goes, in the next step, then player 1 will win. So this is the construction that we have. And this is called the attractor construction. So we create A1 based on A0 by putting all the vertices that player 1 can force the game to go to A0 from them. And then we continue this. So let's say that I know that in AN-1, player 1 wins. So I define AN as everything that I already know player 1 wins at, plus all those vertices that player 1 can, from which player 1 can go to the winning set in one step, plus all the vertices in which player 2 has no choice but to let player 1 win in one step. So this is the sequence of sets that I define. And then I just define my attractor A as the union of all these sets. Okay. And now I claim that all vertices in A are in the winning set of player 1. So I claim that no matter where in A you start the game, player 1 will win. And that's, I think, quite obvious from the construction, right? Because if you have a vertex, let's say V, which is in A, then there is some index I such that, get rid of this. So if V is in A, then there is an index I such that V is in AI. And if V is in AI, by definition, it means that either V is a player 1 vertex, and in one step you can go to AI minus 1, or vertex V is a player 2 vertex, and in one step you are forced to go to AI minus 1. In any case, you can just do an induction and show that after I steps, you end up in T, in A0, which is T. So we can be sure that if we are in an attractor set of player 1, then we are in a winning set, right? So every state in A is a winning state for player 1, which means that if you start the game anywhere in A, player 1 has a strategy to win no matter what player 2 does. Okay, but are these enough? So can there be any other winning states for player 1, any other winning vertices for player 1? Or is A everything that we need to compute? In other words, my question is this. So if I'm in V minus A, if I'm in a vertex that is not in my set A, in my attractor, then can I be sure that there is no winning strategy for player 1? And the answer is actually yes, because there is a winning strategy for player 2 for this objective. So according to the duality, we know that if the objective of player 1 is to reach T, then its dual for player 2 is to stay in V minus T. So we want to have a zero-sum game. Player 1 wants to reach the states T. Player 2 wants to make sure that we always stay out of T. We always stay in V minus T, right? So we know that if we start this game from anywhere in A, player 1 wins. But now let's say that we started it from somewhere outside of A. I want to show that player 1 cannot win. Okay, I do this by defining the concept of a trap. So a trap for player one is basically a set C of vertices that correspond that has these uh, three conditions. So the first property is that it does not intersect with the target set T. The second property is that if I am inside this trap and if I am at a player one vertex, then I have no way of exiting this trap. So player one is trapped inside. If he's in C and he has a choice, we are in a vertex of player one, he can't take us outside of C. And in case of player two has always the ability of keeping player one in C. So if we have a vertex that is in C and V2, then there is at least one successor vertex that is also in C. And this is the definition of a trap. Well, according to the definition, I mean, it makes perfect sense, right? If you are in a trap as player one, you can never reach your target T because there is no target in the trap. And in every step, you cannot exit the trap. And in every step, the other player has the ability to keep you in this trap. Now, by just doing a simple definition chasing, you can see that V minus A is a trap. So what this means is that not only player one does not have a winning strategy outside of A, but actually player two has a winning strategy for the dual objective, which is the safety. So this process gives us an exact definition of which states player one can win from for this objective, for the reachability objective. And this part proves that these are the only states from which player one can win. And of course, in the next session, we will make this algorithmic. It's easy to turn this into a linear time algorithm, and we will see that. And again, safety is the dual of reachability. So whenever you want to decide safety, you can just dualize it and then decide reachability. Okay, we are almost running out of time. We have very little time, so I'm just going to give you a very rough overview of how this can be used in verification. So why is reachability and safety even relevant to us? So consider a case where our two-player game actually models our programs. So you can imagine that in any program, there are some things that are under the control of the program or the system. And then there are other things that are under the control of the environment. For example, the input that some user gives to your program is not under your control, it's under the control of the environment. So it's very much a two-player game. And at every state of the game, either your program decides what to do, for example, decides how to resolve non-determinism if your program is non-deterministic, or it gets some input from the environment or the user. And you can basically model these things as two different players. And you can always think of it as abstractly saying that your program wants to work correctly, but the user or the environment, which is player two, wants to do something that crashes your program. And your goal is to verify which side can be successful. And the verification is basically solving this game. And by solving this game, I mean figuring out from each vertex which side has a winning strategy. Now, to be a little bit more concrete, so let's think about the reachability objective. Let's say that you want to reach a target state or a set of target states T. It can actually be used for proving termination. For example, if T is the set of states in which your program terminates, then reaching T is the same thing as termination. It can also be used for proving that the program is incorrect, proving that the program has a bug. And this is basically very easy again. So you model the set of all of your undesirable states, all of the states that can lead to a bug, you call them T. And what you want to do is that you want to prove that your program can reach T, right? And then the idea for safety is, of course, the dual, and you will see this dualism over and over again. So you can prove the absence of bugs using safety. So if you let T be the set of all desirable states, all states which are not leading to a bug or an error, then safe of T is basically, if you can prove this, if you can prove that player one has a way of ensuring safety in the set T, you have basically proven the absence of bugs. And that's also called safety naturally. And of course, you can prove non-termination. So if T is the set of states, if V minus T is the set of states in which you terminate, in which the program terminates, then safe of T is basically the objective of non-termination. So we can model real-world verification objectives in terms of our game objectives, in terms of our two-player games on graphs. Okay, but do you see any problem with this? There is actually a huge problem. If you think of it from the perspective of what we had in the first module of this course, which was when we were defining programs themselves as transitions between different states. So what I'm saying here is basically that you can get the graph of transitions in your program, which is, for example, given to you by your operational semantics. And you can say, okay, you have two different types of non-determinism. There is the non-determinism that you control or player one controls, and then there is the non-determinism that the environment or player two controls. And what you want to do is basically you want to decide reachability objectives or safety objectives. Okay, so there is a very important disconnect in here. Can you see it? Yes, so how can we capture variables? So basically the idea was that we put, well, in our operational semantics, we had a state for every valuation and every remaining piece of code, right? So our states actually captured our variables, but the problem is that the variables can have infinitely many different values. So basically our state space, if we think of it in terms of, for example, our operational semantics, our state space is infinite. But in this case, what we were doing was that we were solving these games for a finite graph. So in the very first slide, I think when I was defining the arena, I said that our graph game is always finite. So how do we actually handle infinite state space? And I'm just going to give you some pointers here. We will come back to this hopefully by the end of the course. But there are two ways of handling infinite state space or large state space in general. Because there is also the case where your variables are finite. For example, you can have, I don't know, 64-bit integers. So that's finite, but it's just too large. And you can't even create the graph, right? So there are two ways of handling these large or infinite state spaces. One is what's called abstract interpretation. And the idea is that basically, instead of working with concrete states from your operational semantics or from any other semantics that you have, you just group these states and merge a lot of them into the same state. And using this idea, you make your state space finite. That's the very basic idea of abstract interpretation. And the problem is that, well, what you get is basically an approximation. So you're sacrificing the completeness of your approach. And the second approach, which doesn't do this, is to basically handle infinite sets. So the idea here is that we were computing these sets, A0, A1, AN, so on. Instead of concretely computing every item in these sets, we can define each of these sets by some symbolic computation. So for example, I can say that A1 is the set of all states where I'm at line 5 of the code, and also these logical constraints are satisfied. And based on that, I can symbolically compute A2. And based on that, I can symbolically compute A3 and so on. Now, the problem with this is that the process never ends. So again, you're doing an approximation, you're doing like n iterations. So this one is sacrificing termination. And there is no way around this problem actually, because we are again back to Rice's theorem. And Rice's theorem, remember, it says that every semantic property of programs is undecidable. And because of this undecidability result, we cannot really have any algorithms that handle the infinite state space perfectly and also terminate. So you have to either compromise on your completeness or you have to compromise on the termination of your algorithm. But in the rest of this module, we're just going to assume that our graphs are finite. We are going to see how we can solve different objectives. So we saw reachability now. We can actually turn this into an algorithm fairly easily. In the next sessions, we will also see Bookie and then parity. And I'm not really going to cover abstract interpretation or symbolic execution in this course, unless we have a lot of time left at the end of the course. If you're interested in those things, there are many textbooks about them and you can read it, and there are many different ways of doing each one of them. So there are many different abstraction domains. But for now, we will just focus on finite graphs. And in the next session, I will talk about how to do Bookie. And then we also have other modules in this course which basically give us an automata view on the same problem and also a logical view on the same problem. So right now what you're seeing is the game view of the verification, but there are two other viewpoints as well, and we will see those viewpoints during the course. So are there any questions? Come on, we covered so much stuff. Can you really not have any questions? Okay, so I'll just say the thing that I said at the beginning once again. Please take the survey. I really want to know how the course is working for you. And also, please write to me if you don't have the result of your first homework by the end of tonight. And have a very good day, and bye.